Because now we have a lot of noise, background noise. Let me give you one hint. You see two lines, a thin line, this, and thick line, this. Why? Okay, I better help you, I think. So first look at the thin line. So what you see is the current increasing exponentially. This is the first avalanche. Yeah? At this point, all the electrons move into the anode, and then the current drops to zero. At that point, we have a new starting electron, which creates an avalanche, moves into the other electron. So in drawing it with these peaks, we assume that the moment an avalanche reaches the other electrode, the next starting electron is being produced. So one avalanche reaches the other end, and then at that point in time we have the next electron. Probably it's not going to be that precise. The probability of having a new start electron, of course, is largest when we have the highest ionization, which probably is when the avalanche reaches almost the other side, because then we have most ionizations. Yeah? But it's not so black and white, of course, in real life. So also that means that also during its movement to the other electrode, the first avalanche will probably already create sometimes a follower. So at some point in time, maybe we have two avalanches moving. One is already here and the other starts here. Yeah? So that's why in real life we will see a current that goes more like the thick line, yeah? Which eventually moves then to this constant value here. Yeah? That's the thing that you need to know about this. So this is photons. No, is this photons? What did that say? Feedback here, is it by, this is the feedback by photons, yeah? Or what do we think? This is a good question. Yeah, I just thought of it because I was a bit confused myself, but what do you think? Is this feedback by photons or by ions?
Maybe if it was by ions, it would take a while to begin again.
Yeah, correct. This is how it would look like for ions. So we have first avalanche, all the electrons, they move away, but all the ions are still there because they are so slow, remember? So then all the ions, they start moving to the other end. And then only here, when they have arrived at the cathode, most of them, they create the next starting electron. So the feedback process is much slower. And you get something like this. Okay? So for instance, here you have some numbers. If we have an electrode gap of 1 centimeter, 10 millimeters, then roughly the time that ions need to cross the entire gap is about 10 microseconds for electrons to cover the gap is 10 nanoseconds. So the electrons are 1,000 times faster than the ions. Let alone the photons. Okay, feedback by photons. And analogy to alpha, which is the ionization factor, we define a factor theta, which is really the number of atoms per unit of length that is excited, now not ionized but excited by the fast moving electrons. Every excited atom will transmit a photon theta. So theta is also equal to the number of released photons per length of path dx in direction of electric field. These photons, as already mentioned, They will not move in a direction or against the direction of the electric field. Of course, they will move in all directions. Yeah. So only a part of these photons, part G, reaches the cathode. Yeah. Moreover, the part mu of the photons is absorbed by the gas. Because we have the gas, and the gas also absorbs photons. So some of them are captured. So that the number of photons, while they move in the direction of the cathode, decreases also exponentially. This factor here. Yeah. When finally the remaining photons arrive at the cathode, the part delta of these photons has enough energy to be able to release an electron. Yeah. So what do we finally get? We get the total number of electrons now is n0 exponent alpha x. That's what we already had. That's the average times theta. So it's the number of theta is the number of excitations that any electron produces per unit length, times G. G is the geometrical factor, so the number of photons that go in the direction of the cathode, and then this loss factor, because the number of photons is captured by the gas. And the delta, finally, that's the number or the percentage of electrons that has enough energy to liberate the electron from the cathode. If you put all of that together, we finally get a condition for breakdown, which is shown here. We have now capital gamma. This is the capital gamma in Greek times. This is the number of electrons created in the first avalanche. Should be larger than 1. So now we have in this large gamma all the feedback mechanisms that we can have. So due to photons and due to positive ions. And again, we have the same story. This feedback should be larger than 1, this total. Or alpha times d should be larger than this factor. It's really very straightforward, although the equation seems rather complicated maybe. Too close. To join you here, if you don't mind. So if you look at some values of gamma for different combinations of cathode material and gas, we need both, because different gases give you different, they capture different amounts of photons, so it makes sense that different gases have different feedbacks. Different cathode materials also will give you different feedbacks, because the amount of energy needed, for instance, to get an electron out of aluminum is probably different from the amount of energy needed to liberate an electron from copper. Yeah, seems natural. So we see that we have different feedback factors for different combinations of materials and gases. So the values here are not important. What is much more important is that you realize that both in this breakdown mechanism, both the material of the cathode and the type of glass are important. And why? Okay. What I've described now to you, this breakdown mechanism with these two types of feedback, that's called the Townsend breakdown mechanism. Townsend was a British guy, maybe in the 20s, almost 100 years ago. And he described this kind of breakdown mechanism the first time. And the three things you need, the three stages are, again, starting electrons, multiplication process by avalanches, and the feedback. These are the three conditions for breakdown. If one of these three is lacking, there's no breakdown. As I said before, we can have the conditions for a huge multiplication process, but if there's nothing to multiplicate, if there's no starting electron, nothing will happen. Huh? Or if a feedback mechanism is lacking, maybe we have get some short current pulses, or that's it, no breakdown. Yeah. Okay. Now, no questions about this part? I don't think so. Okay, but I promised you I will lead you all the way to breakdown, to condition, real condition for breakdown in terms of parameters. So we've already seen that we can say, okay, this is the condition for breakdown, alpha d equaling the logarithm of 1 plus 1 divided by the feedback factor. Okay. We've already seen that we can express alpha as a function of pressure and electric field and two constants. Yeah. So we put this part in here and we rewrite the whole thing because we want to know the breakdown voltage. That's something tangible that we can work with in practice. How do we get from these two equations to breakdown voltage? Well, let us assume that we're working in a uniform field, uniform electric field. In a uniform electric field, we know that electric field is voltage divided by distance. Yeah? Okay. Now, here's the electric field. So if we exchange this electric field by voltage divided by distance, if we work everything around, finally we get this for the voltage or breakdown voltage. We get this relation. You see, of course, the two constants, P, pressure, and distance, and the feedback factor. So which really means that the breakdown voltage depends on two factors. Let's see, the gas pressure and the electrode distance. Yeah? All the other things, it's constant. Gamma is constant, A is constant, and B is constant, depending on type of gas and type of electrode, but they're constant. Yeah? So you see that P and D are always nicely together here. And now I get back to the thing I said before. I said this is a lecture about gas at low pressure. Yeah? So what do I mean now with low pressure? Not really low pressure, but the low small product of pressure times distance. Because in elaborations on breakdown, the pressure can be exchanged for the distance. A decrease of pressure has the same effect as a decrease of distance. In fact, yeah? You see that directly here in this formula. Yeah? Okay, but we don't like to work with formulas. We like to work with graphs, or I like to work with graphs. Then it's immediately visible what happens because you can already figure out there. Maybe there's some kind of a minimum to be found for the breakdown here as a function of P times D. Yeah? If you're good at math, you can figure it out. Okay, let's plot it. Okay. These are three plots for different gases: air, neon, and hydrogen. We plot UD, the breakdown voltage, as a function of the product of pressure and distance, gap distance, electrode distance. And you see that indeed there is a minimum. This is again torr centimeter, but it's really product of pressure times distance. We have a minimum in the breakdown voltage for any gas, in fact. And you see that the shape of the curves are identical, almost identical for if we change from one gas to the other. The thing that changes is the location of the minimum breakdown voltage. Yeah. You see that also the minimum breakdown voltage itself, the value of the minimum breakdown voltage, it doesn't change that much. It's around 350 volts. That's interesting in a sense, because what does that mean? That if we are below, if we use voltages below 350, we will never have a breakdown. It's not possible. For any condition, we can make the distance between the electrode incredibly small. So maybe you think, okay, we will get breakdown. No, you can forget about it. This curve tells you that if you are below 350 volts for air, whatever you do, there will not be a breakdown possible. So that's what it says. Yeah? There's no way around it. The interesting thing is that looking at this, it makes you wonder how these lights that are now out here, off, sorry, how can they burn? There's a gas, they're gas-filled tubes, and when you switch on the light, there's something going on there. It's a gas breakdown that you see there. But we only have 230 volts here, don't we? Here. But we need voltages which are probably above 300, 350. So how on earth can we get a breakdown in these tubes?
There is a starter.
There's a starter, yeah. You know all about the starter at the end of these tubes? Kind of capacitor?
Yeah.
What does the starter do? It starts the process, but how does it start the process? I think you know.
Yeah, depends. Either it's electronical starter or it's the older one. There are capacitors.
Yeah, but the end effect is the same.
Yeah, well, they change the voltage, or since they're capacitor, it charges, so the voltage is higher and also the frequency changes a little bit. So there's some kind of high frequency breakdown or something like that.
Well, the high frequency maybe is not so important, but the high voltage is.
Yeah.
So for a short amount of time, you create a transient, a voltage which is above this minimum value. The process starts, the ionization breakdown process, and then it can continue at a lower voltage. But you need to cross the line, and that is this line, in fact, first. That's why you have the starter. That's why these things can work. Huh? Isn't that nice? Maybe not so nice, but anyway, that's how these things can work also at 230 volts. One of the things I could ask the students at the exam, let's see if I get all the attention now, is please explain to me why we have a minimum here, why the breakdown voltage goes up here to the left and also to the right. You think you can do that?
The pressure is also inside the logarithm and also outside of it, so it's the same thing as we said, that it's diminishing the alpha as well as it's increasing the alpha. Yeah, it has to be.
I think you can do it. What?
Okay, increase the distance.
Okay, the difficulty here is that we have a product. So, okay, to keep it simple, let's first keep the distance constant, yeah, and then change the pressure. Yeah? So left of the minimum, we have a very low pressure. So what does it mean? Very low pressure means huge mean free path. So electrons will get enough energy. But probably they will not need anything to ionize. Yeah. So breakdown voltage goes up there. If we go to the right, it's the other thing. Plenty of opportunity to meet other atoms, but not enough energy. So we need to increase energy by raising the voltage again. So hence the breakdown voltage goes up. Okay? You can figure out by yourself now what happens, how you can explain this if you would keep the pressure constant and vary the distance. Yeah? This, I think you should be able to do that. I'm not going to explain that. No. Yeah? It's a nice exercise to do at home. I also might use this as the question at the exam. Yeah? what I want to. So this is really very helpful, in fact, in practice. Quickly scan that. Because suppose that we have to design like construction in a high voltage lab where you have air around 1 bar, yeah, so we know the pressure. And for instance, we have two, let's say we have a uniform field, 2 metal plates or so. And we say we want to avoid breakdown, and we want to use, let's say, 1 megavolt in a lab, uniform field. What should be the distance at 1 bar? Okay. Where do you think we have to look? To the left of the minimum or to the right in this particular example? Probably to the right. Okay, let me help you. Probably to the right. Yeah. So this is let's say 100 kilovolt. That is still in the graph. 100 kilovolt is here. 10 to the 5th. Okay, air. We're here. So we need 10 to the 3rd torr centimeter. Okay, we have to convert that into bars and millimeters. So from there, we know it's 1 bar. So we know the distance that we should have in order to get breakdown. So we can increase the distance a little bit and we avoid breakdown. This is how we can use it. Or, for instance, when we remember the cavities in insulation, I said, okay, of course we want to avoid that if there are cavities in cable insulation, that they will lead to small breakdowns there. So the point is, what is then the breakdown voltage of such a small cavity? If we assume, again, 1 atmosphere pressure, yeah, and we can then look for different sizes here of cavities, what is the breakdown voltage? Yeah. And then we can calculate from the voltage we apply on the cable back to the voltage across the cavity, whether this voltage would lead to a breakdown in the cavity. This is how often people use the Paschen curve, the Paschen's law. Okay, but now you know how this, where it comes from, this breakdown value, at least in this mechanism, which is gas breakdown at low pressure. And again, low pressure means a small value of the product of P times D. So what is the small value of the product of P times D? Usually we say if we are below 5 bar millimeter or something like that. So in ambient air here, it's 1 bar. Distance should be smaller than 5 millimeter. Then we can still talk about low pressure. Or, in other words, for most constructions in ambient air, we have to talk about high pressure. Yeah. Okay. You will see that in the literature for gas discharges, there's a lot of German, or many Germans worked on that in these years before the Second World War. So that's the reason. Paschen, he was German, or at least German speaking. I don't want to make a mistake here, maybe he was Austrian. Here you see the Paschen minima, so the voltages and the location of the minimum voltages for different gases. You see that for many gases that is let's say around 300, maybe just 400, but the range is not so large. Here you see the position of the minimum. Now it's easier to remember units, bar, micrometer. One thing for air, Luft, It's air in German, Luft in Dutch. You see that the minimum occurs at the product of P and D about 7 bar micrometer. So the minimum breakdown in ambient air, 1 bar, is at a distance of 7 micrometers between the electrodes. Okay. And this is the not Paschen's law, but this is the Paschen curve for air. Mind you, this is a logarithmic curve. This is the one that's much easier to handle because now we have bar millimeter here. Now we're on safe terrain, I would say. Here you see that this is in the peak value of the voltage, breakdown voltage in kilovolt. So let's look at the minimum. Here we see this is 10 to the minus 1 is 0.1, 0.2, 0.3. This is about 0.35 kilovolt, about 350 volts. And the location is about 7 micron there. Yeah. But for any distance and any pressure in air, you can now figure out what is the breakdown voltage. Huh? And we go to about here, this point, or really about somewhere here, 5. And then it becomes dotted here, because there we get into the region of gas breakdown at high pressure. Okay. Small summary of the Townsend mechanism. We will compare that at a later stage with the mechanism at high pressure. Low PD. The mechanism is that we have accelerated electrons ionize gas atoms and they cause avalanches, and we have feedback at the cathode by ions and photons. The material of the cathode avalanche, the type of material affects the mechanism, because the change in cathode material changes the amount of energy that you need to liberate the electrons, so it makes sense. The gas has an effect on the mechanism. If you would be able to film the breakdown mechanism, just visualize it, you would see a kind of diffuse light which would fill the entire space between the electrodes. And because, remember, feedback by photons, photons will go in all directions. Yeah? So if the first avalanche is here, there's some photons going here, or maybe the next one will be here. So gradually the entire gap between the electrodes will be filled by avalanches. Yeah? So it's a diffuse mechanism. This is important. The amount of energy involved is relatively low. In fact, these tubes there, you can touch them. Yeah? Not the ends, but the glass. Yeah? So that is low temperature, low energy. Time to break down usually is in the order of microseconds, especially when you have to rely on feedback by ions. They're slow. Yeah? So that summarizes roughly this mechanism. Oh, and I'm too fast. Can you imagine that? I can already go to next week. You have this funny smile on your face now, a bit scared, but also a bit laughing. Any questions about this? Perfectly clear. Yeah. What about lightning? Huh? Is that a breakdown? Is it a breakdown at high pressure or low pressure?
High pressure.
High pressure. Yeah. There's a special lecture on lightning in a few weeks from now. But maybe we move now to where is it? That's at high pressure. this I can make a start. We still have 15 minutes. You see, we have to deal with a different mechanism now. This is which is called the streamer mechanism, as opposed to the Townsend mechanism. Of course, I will compare the two, so you see what are the differences. I will speak a little bit about spark and arc. What's that? Breakdown in atmospheric air is very relevant, of course, because we have a lot of high voltage constructions in atmospheric air. A special topic is compressed gas insulation. Switchgear, for instance, uses SF6. We make good use of the electronegative properties of some gases. And the last item will be corona. I spoke about it, many of you have heard about it. Probably that will be next time. The point is this. We've seen this. This is the Paschen curve. What happens there to the right when we have the broken line? Larger when we have P times T larger than 5 bar millimeters. Very relevant because that's the situation we have here. If we first look at the characteristics of such a breakdown, that's another way of looking at it, just looking how a breakdown occurs in ambient air, we will see that the time to breakdown is far, far shorter than the time to breakdown for the other mechanism. That must be the reason. Secondly, we see that the breakdown voltage is no longer dependent on the cathode material. We can exchange metal of one of the electrodes